Okay, Year 12, here is the next section of Chapter 2, which is about looking deeper. So here's Robert Hooke feeling the strain. Why? Because of the stress of Isaac Newton dissing him and saying how rubbish he is. So what we're going to do is kind of use an analogy, and it's quite easy to use this analogy to keep clear in your head what's going on. So I'm going to introduce you to two phrases, strain and stress, etc. So what we need to do is just make clear in our heads, but it all links together, and this is where we start looking at properties. So within the chapter itself, what we need to know about is what the difference is between stress and strain, units and details like that, but more importantly, how is that important for materials? So stress. Stress is basically, giving back to my picture here, what Robert Hooke is doing to the material. Yeah, maybe this is his teddy bear or an early version of stress ball. He is stressed. He is doing something to it. He is going to stress that material. So the definition that, again, you can be asked to do is force per cross-sectional area. So it's not just you pulling it or pushing it, but it's actually how concentrated that force is. So in a way, it's a bit like pressure, because it's force per unit area. Okay, so compressive, if you are compressing it, that tends to be called pressure in a normal everyday speak, but actually it's compressive stress. And if it's tensile stress, then it's stretching instead. So equation-wise, it's nice and straightforward in that the actual symbol is a lowercase rho, and what that is, sigma rather, lowercase sigma is the force over the area. Very similar to pressure, okay, the same kind of thing. Now, we start to link about things, because if we are talking about how much force it takes to break something, it depends how big it is. If you are trying to stretch cotton, it doesn't take much force to snap it. But if we have a bigger cross-sectional area, okay, then if we move into something like string or rope or thicker, then it gets a much bigger force that's needed to snap it. However, the material itself will be as easy to snap because it's made of the same material. So whatever the material is, that has a stress that you can cope with. The largest it will get, commonly used phrase is UTS, or ultimate tensile stress. That's the biggest stress it will take before it breaks. Now be careful, it doesn't mean it breaks at that stress. Some things, for example, if you flex them, they will flex and flex and they'll get weaker. So after the first flex, it won't take as much force. You're never going to be able to stand as much stress on it again. You'll not be able to put as much force on it again. Okay, so the ultimate tensile stress is the maximum stress at any point of a material. Give you a bit of a scale on this, because these are, they don't seem like big numbers. If we're starting to talk about materials, then actually what we have are huge numbers, because what we're talking about is, for this unit, is area as meters squared, because that's an SI unit. So newtons per meter squared, okay, or measured in pascals, which is how you'll usually see it. So again, just the same as pressure. So yeah, 85 million newtons on every meter squared will cause it to change shape. Stainless steel, strange enough, a lot bigger. Okay, but 85 is quite big for nylon, because you think of it as quite a flexible material. Kevlar, much harder to actually distort, needs a much bigger force. So it's actually 3,100 meganewtons for every meter squared, or 3.1 giganewtons if you prefer. But most things tend to be meganewtons, so again, you'll see that unit quite often. Now, if you stress a material, then it will change what it does, and this is where strain comes in. So this is a really important phrase, really important idea. You put the stress on something, and that thing feels the strain. If you want the analogy, teachers cause you stress and you will feel the strain of having to prepare for exams. Okay, so you are not stressed, someone stresses you. Yeah, and then you feel the strain, you're put under strain because of it. So you feel like you're being stretched. So this kind of gives you this hint on what strain is about. And strain is has got this symbol called epsilon. Don't need to know that, but again, it's in the data book. But it's this idea of stretchiness. Okay, so it's a nice simple idea because this is basically a ratio. Extension divided by the original length. So a long thing will stretch more. That was the hint from last time when we looked at the ideas on springs. Okay, if I just take you back to there, and I've lost it now, there we go. You know, a longer spring will stretch much more. So it links in with this idea of strain anyway. Twice as long should stretch twice as far for the same force that you've put on it. So that force spread over or concentrated over a smaller area, spread over a big area, will cause this to change length, and this is just a ratio. So for example, steel will stretch 0.01. Now if you want it as percentage, multiply that by 100, that's going to be 1%, which I put in here. Okay, spider silk, which is made of a lot, is much stronger, but it is stretchier. Okay, so it will stretch a lot more, up to about 0.3, so almost a third of its length before breaking. So 30-ish%, okay, 15 to 30%. Some things, like climbing ropes, for example, depending what you're using them for, will have different properties. So both climbing and hauling ropes, so ones that are used for lifting things that aren't stretchy, will both basically have about the same stress that will take. However, if you're a climbing rope, you want it to stretch, so you want a big strain, and you'll actually get around about 0.5. It will stretch half as long again from its original length. Whereas a stretchy rope is useless for pulling people up, so rescue ropes only stretch by 0.05, okay, so about 5%. So depending what you want it for, doesn't necessarily make it any weaker, it just changes its behaviour. Now crucially, and this is a trick question that you often see, strain has no units, because it's a ratio. Meters divided by meters, centimeters over centimeters. Doesn't matter what they are as long as they're the same. Now, what that can do is when we put those two together, what we do to a material and then how it behaves gives us really interesting graphs, and it's the graphs that are really important about this. So here we have two materials. We haven't said how far they go, so you know, they might go up to the same maximum stress, we don't know. But one of them is much stretchier than the other. So for the same force per meter squared, one is going to stretch much more. So it's a much greater strain. So this is your stretchy material. This is your stiffer material. Yeah, so for the same force, it doesn't stretch much. And depending what you want it for, you're going to choose one material or the other. Okay? Wings on an aircraft, for example, you don't want them to be floppy. You want them to be quite stiff. So when we look at these, it gives you a bit of detail on this, but more importantly, it gives you a bit of a hint on how to treat with these. So if you put dotted lines on graphs, they're much easier to, you know, across at a level, or maybe think of it as going up, whichever's easier for you. You can work it through. So perhaps you're the opposite of me, and you kind of go, okay, for this amount of stretch, one needs a bigger force, so that's the stiff material. That doesn't need much force, it's the stretchy material. So you could do that, or for the same force, which one stretches more? Same thing, two ways of thinking about it. Okay, so the interesting bit is then there will be a limit which links into what you did at Hooke's Law at GCSE with the elastic limit. You'll get to a point at where it starts distorting and this graph stops being straight. If that happens, then what you've done, as it mentions here, you get a permanent deformation. It's deformed permanently. Okay, this is a temporary deformation. You stretch it, and then you take the force off, and it goes back to its original length. Okay, if you keep stretching it, adding a bit more, but it keeps going back, you know it's within its working life, not a problem. But if it gets to a point where it starts to bend over, then when you let the weight off it, when you take the force off, what you'll find is it's now permanently longer than it was before. Okay, and that's your deformed permanent deformation bit.